Welcome to the 24th video of Quantum Mechanics Done Right, the shortest path from novice to researcher. In this video, we're going to talk about Chapter 19, which is Applications to Chemistry. I have a nice image there of a chemist working with some kind of chemical reaction. And then here is a beautiful image of Rovibrational spectroscopy, which is one of the topics that we cover in this chapter. Chapter 19, Applications to Chemistry. So we start our chapter off with a discussion of Rovibrational spectroscopy. What we have is we've already solved the harmonic oscillator and we've solved angular momentum states. And that's really all you need in order to understand Rovibrational spectroscopy, except you have to go a little bit beyond harmonic oscillator. You have to be able to solve an anharmonic oscillator, but we already have done that as well with the Morse potential. So in order to discuss Rovibrational spectroscopy, we use the Morse potential as our paradigm, and on top of that, the rotational states that a dimer molecule has. And that allows us to go through and look at the selection rules, look at what the spectroscopy looks like when you have so-called fundamental and overtone spectroscopy, and even hot spectroscopy. So when you have this spectroscopy, you can learn lots of interesting things, such as the distance between the atoms and the molecule and so forth. And it might even be one of the most accurate ways of measuring interatomic distances in molecules. So it's a very important spectroscopy in chemistry. Next up, we cover the asymmetric top. The asymmetric top is something that is also a really nice application of the things that we know with regards to angular momentum, but it's kind of a hard problem. It isn't one that easily fits into the kinds of things that we've been doing, so we can't just jump to the answer. So most quantum mechanics textbooks tend to shy away from it. The chemists, of course, don't. So if you look at an advanced textbook in molecular spectroscopy, they'll cover it. They cover it from a very concrete fashion. Everything is differential operators, and I find that's a little bit hard to follow, and it gets very, very messy. If you thought working with angular momentum and spherical harmonics was difficult, you have an extra angle because there are three angles that you need to describe the rotation of a rigid body. They're the so-called Euler angles, and that makes the whole calculations even messier. So now you have three differential operators you're working with. Now in physics, there are three textbooks that I'm aware of that really go through the asymmetric top. This is done by Weinberg's quantum mechanics text. I think you have to get the second edition in order to see it. It's done in Landau and Lifshitz. And then it's done in a book that is really on angular momentum for experts by Biedenharn. And I'm not really satisfied with any of those derivations. They do it in a way that I like in working with operators, but they go through the derivations really, really quickly. And at some places they just say, well, it's obvious this is what the commutation relation is without actually calculating it. And I don't like that. So I found a new way of doing it in this section, and I think it's a really nice way to do it, clear, easy to understand, and we work out every commutation relation exactly, so there's no confusion or misunderstandings about how anything works. Then we talk about the hydrogen dimer. This is, again, the simplest molecule that you can have. We talk about it in a Hartree-Fock perspective. And then we talk about Hartree-Fock in general for more complicated molecules and how that would work. And then we do something that is, again, rare to find in quantum mechanics textbooks. We talk about the coupled cluster approximation. This is one of the absolute coolest ways of doing quantum mechanics that is out there. This is something that the chemists have really worked with and developed. It actually originally comes from physics, from nuclear physics. But it is such a cool idea, and it's cool the way that it works. You're essentially doing a variational calculation, even though coupled cluster is not a variational calculation, but you never create the state. You just work with operator manipulations, and of course it's the Hadamard lemma. You work with those operator manipulations to do your calculation. It's absolutely beautiful stuff, and this is the gold standard for quantum chemistry calculations. It is what is typically used when you need an accurate calculation. It's not perfect. It has some issues to it, but it is a useful thing to know how it works. And then we talk about unitary coupled cluster. This is interesting because this is the way you would do quantum chemistry on a quantum computer. And so we talk about how that works, and we talk about some of the different issues that arise in understanding how unitary coupled cluster works. We also talk about this beautiful identity that you get. It's a SU2 identity that allows you to work with the individual factors that make up the unitary coupled cluster ansatz in such a way that you can efficiently apply them on a quantum computer. And then what we do is we show how coupled cluster and unitary coupled cluster are related. And for this, we need to use exponential disentangling identities. And it's really cool the way it all fits together, and we see the real power of our identities. And I tell you, because so many chemists don't know these identities, these problems have sat unsolved for a long period of time, but in the process of doing this work, I figured out that they could be applied here and wrote papers on it. So the kinds of techniques that we work on this book really lead you into being able to do things that no one else can do. And I think that that's a really cool aspect of this way in which we do quantum mechanics. All right, guys, let's go browse through the chapter. So we have chapter 19, Applications to Chemistry. Here our quote is from Pablo Picasso. The one who finds something, no matter what it might be, even if his intention were not to search for it, at least arouses our curiosity, if not our admiration. Now, Picasso is an artist, but I believe that that is a really wonderful way of describing scientific discovery as well. Science is all about finding something that other people don't know about. That's what new knowledge creation is. And this is a wonderful quote that explains how that works. So we start off with Rovibrational spectroscopy. That requires us to look at the Morse potential. So we come back and we look at the Morse potential in more detail than what we have done before. In particular, we use this in order to talk about the selection rules that you have in Rovibrational spectroscopy. This is an image of what the Morse potential looks like. The fundamental spectroscopy is just the transition from the ground state to the first excited state. But when you have an anharmonic oscillator, you can also have transitions to the second or third excited state, and those are called the first and second overtones. If you heat your molecule up to really high temperatures, you can excite higher energy states, and then you can have what is called hot spectroscopy, where you're doing an excitation from an excited state to a higher excited state. There are interesting things you can do in analyzing the data that tells you whether or not the Morse potential is a good fit to it. The criteria is that these last three numbers would be all the same, and you can see they're pretty close to each other, so the Morse potential is actually a pretty good fit for this molecule, which is hydrogen chloride. This is the Rovibrational spectra of hydrogen chloride. The top is the fundamental, the bottom is the first overtone, and it's a beautiful spectroscopy, but by carefully analyzing it using our quantum mechanical ideas, you can understand why the spectra looks like it is, why the spacing is nearly uniform, why there's no line in the center, why there are two peaks, and so forth. And so it's wonderful to use our quantum ideas and get a full understanding of exactly how this spectroscopy works. Because it's Rovibrational spectroscopy, there's a rotational transition in addition to the vibrational transition, and so we go through those details as well. We carefully use the factorization method to tell us about the selection rules. And we have a number of other interesting problems that are related to Morse potential, including calculating the wave functions for the Morse potential. There's also a very famous problem that appears in nearly all quantum mechanics textbooks about ammonia, and so I don't disappoint, I put that problem in here as well. Next up is molecular rotations, and as I had mentioned in this chapter, I talk about the asymmetric top, which is a challenging problem to solve, but it actually works out fairly easily when you rewrite everything in terms of average and relative coordinates. And once you've done that, then you have all the right commutation relations. You can work out all of the theory. It's a little technical. It's really not that bad. Some of the equations are long, but it's really not that bad working out the details. And you can very carefully and clearly work out all the commutation relations. You can work out what the Hamiltonian is, and you can then diagonalize it. And so it's wonderful how it all fits together. It's again a really nice application of quantum mechanics to a non-trivial problem, and you can determine what all the different spectral lines would be and so forth. And you can do this now essentially for an arbitrary molecule because asymmetric top is the most general case. Then we move on to the hydrogen molecule. Hydrogen molecule is treated in a standard fashion. It's a complicated Hamiltonian because you have an interaction between the ion cores, you have an interaction between the electron and each ion core, and there are 2 electrons and 2 ion cores, and then you have the electron-electron interaction. It's only that last interaction that makes the problem a many-body physics problem and hard to solve, and so that interaction can only be treated approximately. So we discuss how you set up the wave function basis that you would work with. We look at what is now called a mean field theory and how you sort of construct this best mean field theory, which determines the best linear combination of atomic orbitals to make the molecular orbitals, and how you then fill them according to the Pauli exclusion principle to get you the lowest energy. It is not an exact calculation. This is an approximate calculation, but it's the first calculation that is done for essentially any molecule. So it's important to understand how the Hartree-Fock approximation works in general. So we talk about how that works. We do it in the second quantized format. Sometimes in chemistry books they will work with it with Slater determinants at first, but it's much easier to work with it in the operator formulation. And we talk about how the matrix elements are calculated with Gaussian states and why Gaussian states are chosen. There's a very special property about Gaussian states that allows you to calculate matrix elements, again, using the kind of operator methods that we've been developing in the class. So it's a really nice application of quantum mechanics and the things that we've been doing. Now we get into the coupled cluster approximation. I hope I have made it clear that I think that this is one of the coolest things that's around. I didn't know about it until I started doing some work in quantum chemistry, and it's absolutely wonderful. The chemists are incredibly smart for figuring out how to do this, and I have the utmost respect for this kind of work. It's really fantastic. The way in which it works is you take this operator e to the t, you act it on that Hartree-Fock state, and you're going to try to diagonalize the Hamiltonian. Now, what you would do if you were doing a variational calculation is you would put an e to the t dagger on the other side and calculate that variational energy. But that is a complicated calculation. We don't know how to do it. So what they do instead is they make a Hadamard. They put an e to the minus t. So they do a similarity transformation. That's no longer a variational calculation, but now they can do the Hadamard on that expression, e to the minus th e to the t, and that's exactly what they do. It truncates at the 4th order. So there are lots and lots of terms. It's very complicated. But they worked out very efficient ways of calculating that Hadamard. And then once you have that Hadamard, you then have what are called the coupled cluster amplitude equations that you have to solve in order to essentially diagonalize the matrix. They don't diagonalize the whole matrix. They just diagonalize the lowest row and lowest column of the matrix, which is where the ground state energy sits. So they use this to find the ground state energy. But they don't really get the right quantum state. So if they want to calculate matrix elements and things like that, while they can use that coupled cluster state to do it, it's perhaps not quite as accurate. And also because it's not variational, they don't know that the energy that they get lies above the true energy. Then we get into unitary coupled cluster approximation. The unitary coupled cluster approximation takes the thing that we were doing with the coupled cluster and subtracts the Hermitian conjugate of it so that you have the exponential of now a Hermitian operator, and then it's a unitary operator that you apply. But now that Hadamard lemma doesn't truncate, and so you have to solve it in a different way. So here we talk about that SU2 identity that relates these coupled cluster factors and allows you to come up with an explicit formula for how each of those states act Each of those operators act when they act on the current state. Here's some numerics that I did that show how this unitary coupled cluster works against other kinds of approximations. Unitary coupled cluster is variational, and so because it's variational, you actually find that it does a better job than conventional coupled cluster when the system becomes strongly correlated. And of course, the energy always lies above the ground state energy of the molecule. Then in the last section, we use our exponential disentangling identity to show us how unitary coupled cluster and conventional coupled cluster relate. This is possible because we have this SU2 symmetry for these unitary coupled cluster factors. That means we can use exponential disentangling. And it's really beautiful the way in which this works out. And I think that this is just really cool. It again is putting together a lot of the ideas that we've developed in the chapter, and I like the way it all fits together. Now, I will tell you that we still hadn't fully solved the whole problem in determining the exact relationship between coupled cluster and unitary coupled cluster, because there's a lot of exponential reorderings that have to be done, and it's very tedious to try to figure out how to do that in general. In principle, I think it can be done, and we know all the formulas to make it work. And in the paper that I wrote about this, I talk about how that can be done. But the details haven't really been worked out. And as you know, the devil is in the details, and there could be something surprising that comes about when you try to work out all of those details. Okay, that now takes us to the end of chapter 19. Hey guys, let's do quantum right.